Okay, perfect. So I'll begin with one of the student questions, which is, there is considerable media coverage of advances in quantum information science. Some even dub this coverage as exaggerative hype. What is your position on this stance?
Well, maybe I can jump in and say something, and I would love to hear what Monika and Prineha think. Yeah, there's absolutely a lot of hype today. I think I mentioned this in my talk, and you know, it's not entirely unwarranted. I mean, quantum computing does hold the promise to revolutionize computing as we know it. But on the other hand, we know, as I said, that you know, developing technologies takes time, and it's almost always more time than we anticipate. And so the hype is good in the sense that it reflects a reality that this technology is moving from the laboratory into the commercial space, and that's a good thing. But of course, the overhype part of it is a little bit dangerous because people speak of a quantum winter or something similar where if we don't meet the expectations, the unrealistic expectations that are set by the hype, then we do risk a problem of funding going down, whether that's from the government or from industry, leaving us in a bit of a lurch, trying to, you know, make the connection over the valley of death, as they call it. So, you know, I think that the hype is justified to some extent because this is very exciting research, and there is a lot of promise. But we shouldn't think that everything happens on a 3-year or 5-year time frame just because our government funding agencies require that we make proposals on 3-year and 5-year time frames.
Yeah, I guess maybe I'll jump in and say I don't think we know yet what the killer app for quantum computing is really going to be, right? And so in that sense, maybe it seems like one should worry about all the hype when we're not quite sure where it's all leading. But on the other hand, I think there's no question that, first of all, the field is advancing so rapidly, and there's just fascinating fundamental physics that comes with the question, what happens and what can you do as you start making better and better qubits and wiring more and more of them together? And there's no question that it will lead somewhere interesting. I just think we don't know exactly yet where it is. So we have to try it and find out.
Pri, do you want to add to this?
Well, Will and Monika covered most of it. I agree that there is, you know, a lot of excitement, and I think being cautiously optimistic is a good idea. There are certainly, you know, a lot of people thinking about how you could use quantum computers to find things out about correlated quantum matter that we can't currently do using classical devices. I think it's also promising to think about hybrid quantum classical schemes and see if we can learn more about problems in condensed matter and other areas of fundamental physics. And I think that's you know, showing promise already. I don't yet know how that's going to impact everyone's daily life and how they make coffee. So that's the part that I worry about.
Maybe I'll just add one more comment that I think now is such an exciting time for sort of bringing together expertise from different perspectives. So there are so many different things that we need, making better and better hardware, right? But also understanding that sometimes the people who understand the hardware aren't the same as the ones who know what the problem is that hardware can solve. And so dialogue between different disciplines is so important. And also being able to understand the problems, but also, again, also the capabilities and limitations of the hardware. So being able to sort of bridge these different fields is so important. And I think there's so much room for creativity at this time.
Great, thanks. So the next question again for all of you, and feel free to jump in, concerns material science. So coming from material science and engineering, I'm curious what your thoughts are on how computing technologies can promote the development of the field of materials research. Eventually lead, for example, to the design and synthesis of materials. And each of you had different perspectives on how your approaches can engage the materials community and learn about existing materials. I'm curious how you think it can lead to the design of new materials or the synthesis of new materials.
So maybe I'll jump in with a perspective from, so maybe just at a high level, I think there are different ways in which this field can fuel the design of new materials. We heard from Will earlier about sort of the materials science challenges, right, in making good qubits. So that's kind of some motivation. But on the flip side, I do think there are exciting opportunities from the perspective of quantum simulation. And I think one important thing to keep in mind here is that this is a field that might sometimes be sold as though we were going to like build some lattice model in the lab and that would immediately like inspire the design of a new material. And I don't think that's the right way to think about it. So the way I see it, sort of the field of condensed matter physics, there's kind of a whole realm of condensed matter theory that was kind of inspired by thinking about real materials, but that has grown sort of way beyond what you might encounter in real materials. And that's sort of also grown in the direction where it's convenient to write down sort of simple models, right? To ask which models will capture the basic physics of a real material, or to predict new things you could do, topological, encoding of quantum information and things like that, right? Growing out of sort of inspired by the study of real materials, but growing way beyond that. So I would say in quantum simulators, we have the opportunity now of building in the lab these simple models that nevertheless, because they're many-body systems, the model is simple, but you still can't calculate necessarily what its ground states and dynamics will be. And I would say that the most immediate impact can be in kind of feedback to theory, right? So sort of pushing the development of better numerical methods for modeling quantum many-body systems, right? That is a place where I think there can be a very rapid impact. And then I would say the longer term impact, and I see Prineha nodding, so I hope she'll add in, but I think then the longer term impact is taking the insights that you gain from that or the better numerical methods that you gain from that, and then using that to inspire the design of new materials.
Yeah, so I'll just build on what Monika said, that, as we think about correlations, especially correlations that are really, really hard to capture on even the largest DOE supercomputers. I know this, having written for time on these and done like hero calculations. So I think if we can get knowledge from smaller quantum calculations that we can run on a real quantum device and parameterize other maybe more known classical computational approaches that simulate quantum dynamics, I think that could be really beneficial. We've done a little bit of this in thinking about open systems, and this is some of it is in collaboration with David Mazziotti's group. It's not too far from where Danna, you and James are located, to think about open systems where you're not treating the correlations in the environment and not treating it as lost, but coming back, and truly, quantum correlations that are coming back from the bath. And we found that some of these calculations could actually run very efficiently on even, a 5 or a 20 qubit system. So I think that there's, which wasn't expected. We thought this is going to be a toy calculation, nobody's going to care about it. And they're like, wait, we found something we couldn't actually understand or trivially think about from other business models. And I'm sure there are, other really smart people who'll find stuff that wasn't expected from classical calculations.
Great, thanks. Will, did you have any comments you wanted to add to that, or?
No, I think that was a great, they hit most of the points I would have made. I think maybe one thing I'll add is that, many of these algorithms that at least we know of today, more may come, but they're related to optimization. But the size of the systems we have today just isn't big enough to solve problems that are meaningful in a commercial sense. But that doesn't mean that we shouldn't be working on those algorithms now, because we can design algorithms and we can show that they work. We can show that 3 times 5 equals 15, Shor's algorithm, right? And we can do similar things for the types of problems that we would envision doing in the future when we have a quantum computer that's large enough at scale to really bring commercial advantage.
Great, thanks.
Thanks. Okay, so I'll grab one last question from the pre-submitted questions, and then after that, I think James will grab one from the Q&A. I think that especially with the new the new topic areas for the NSF Graduate Research Fellowship Program. We have a lot of students in chemistry and material science who are thinking about different directions. So what are the growth areas for quantum information science, and how can scientists leverage diverse perspectives and interdisciplinary approaches to tackle these areas, kind of from the lens of speaking to the students, I think?
You know, maybe I can just jump in and say a few things. One of the consequences of quantum information moving to this next phase of development is that the idea of having a vertically integrated laboratory that's going to do everything from the materials growth to the fabrication to the control to the design and making the algorithms and the compilers and actually understanding the problem that we're trying to solve. And, you know, the number of people worldwide who can actually do that is getting fewer and fewer. And I think that that's a good thing, because the reality is that if this is going to become a practical technology, in my opinion, that we need to have diverse opinions and people from backgrounds who study other topics than just quantum information coming and bringing their knowledge and applying it to this new field. And so I think that there's, you know, tremendous opportunity there. And if I had to say, I think that that may be one of the reasons that the NSF may be shifting focus a little bit, is to encourage more people who come from what you might call a non-traditional quantum information background and getting them into this field, because we really need people who understand computer science and algorithms and compiling and chemistry. They know what problems need to be solved. They may not know about quantum computers yet, but that's what grad school's for. So I think there's a lot of opportunity. It's very exciting.
Yeah, I'll maybe just reinforce what I touched on earlier, which is that having both a deep knowledge of a potential sphere of application like chemistry, right, and some of the actual hardware platforms, I think is really a space where there aren't enough people, and I think that could make an amazing difference. And maybe just to be a little bit more concrete about it, I think often people sort of think only in the sort of circuit model of quantum computing, and that's nice because there's a simple formalism, and you can ask what problem might map onto what circuit. But in reality, we have now these devices where we're kind of in this regime, in this kind of early, I guess, this NISQ regime, right? The noisy and intermediate scale quantum devices. I don't love the term because we try so hard to make things less noisy, and the theorists still call them noisy. But anyway, but we're in this regime where, and you have sort of small numbers of qubits, and you're not going to build a full error corrected quantum algorithm. So you have to really think about the question, like, how do you kind of efficiently use or map the problem onto the hardware that you have, right? And so this idea of kind of understanding the problem and the hardware deeply enough to come up with an efficient way of tackling that problem that's matched to the hardware is something that not so many people really have the expertise to do, because you really need to understand both sides. So I think that's a space that I would encourage people to try to get into.
Yeah, I guess by 2 cents on this, yeah, for students who are entering grad school now, I think within quantum information there are lots of things. There's quantum computing, there's also sensing metrologies, work in quantum networks. I think there's a lot to do, and thinking about it from a chemistry perspective is absolutely valuable, and showing intersections between that and, say, various areas of engineering and computer science could be very fruitful. I'd also add, especially for graduate students who are thinking about theoretical chemistry, you should absolutely take a class in quantum information or quantum computing, because you'll find that those two areas will, if they haven't already, in whichever group you're working in, intersect very soon. So that would be, I guess, something you should think about.
Okay, great, thanks. So we'll go to now the Q&A box. And so the first question, I believe maybe Will can start this one off, is concerns the operating temperature for superconducting qubits. It's on the order of millikelvin, which requires non-trivial cryogenic support. How could we boost the operating temperature in the future? And then the question continues, will high temperature or unconventional superconductors be useful for this aspect?
Yeah, that's a really good question. So this object behind me is a dilution refrigerator, which we use to get to these millikelvin temperatures. And 30 years ago, as a grad student, one might be actually spending a lot of time making this thing work. But today, it's basically a commercial item. You buy it off the shelf. And so, of course, there's a lot of know-how in getting the signals from room temperature to base temperature without heating up the device and things like that. But the millikelvin aspect of it isn't an issue today. Now, as we scale up to thousands and tens of thousands and hundreds of thousands and beyond, then the question becomes, how can I control all those qubits while maintaining the temperature at the millikelvin stage? So why do we do it at those temperatures? Well, the answer is that we like to operate at, say, 5 gigahertz-ish. And 5 gigahertz, if you take h bar omega, or hf, H Planck's constant, and equate that to temperature via Boltzmann's constant, you find that the equivalent temperature is about 250 millikelvin, right? And so if I took a qubit that's got a 5 gigahertz transition and put it at 250 millikelvin, I would be saturating it, basically. I would be certainly putting population in the excited state. So that's why we need to be so much lower. So if we want to increase the temperature, one thing we can do is increase the frequency, right, of the qubit. So that's one way to go. But as we spoke about earlier, that may come with some contraindication in terms of the T1 time if you don't think about the matrix element. But on the other hand, with the design of qubits, you can make them largely insensitive to even a very hot environment, provided the matrix element is appropriate. And then the challenge now becomes, can I initialize my qubit into the ground state? And once it's there, basically it doesn't see the hot environment for a very, very long time. To give a common example, like NMR, we do NMR at room temperature, but maybe it's at 50 megahertz, right? So, but that's because the matrix element is so small and we can initialize, or at least we try to, right? So those are some of the trade-offs. Now, in terms of higher temperature superconductors or unconventional superconductors, again, what's driving the temperature is not so much the TC of the material, but it's really the frequency of the transition that we choose for our qubit. That's really what's driving it. But of course, going to higher temperature superconductors allows us to, at least in principle, operate at those higher temperatures with larger qubit transitions.
Great, thanks. I don't know if anyone else has any comments, but I think we'll comprehensively answer that one. So thank you.
Yeah. Okay, I can grab the next question. And we actually have 2 questions that are fairly similar. So I'll do both of those. What are some of the limitations and issues with incorporating quantum computing systems? What are the barriers to running and building these systems? And similarly, what are the most significant hurdles that you believe have to be surpassed for a quantum computer to become commercially available to the average consumer, similar to personal computers today?
Okay, I'll take that very last one and say that there are, quantum computers, both superconducting, trapped ion, and also photonic in some cases, that are available over the cloud. So you can, from your laptop at home, run calculations on these same way you would on any other cloud-based system. Actually, if you're used to AWS, they introduced AWS brackets, so you can get access to these quantum computers. You would of course have to think about what you're running on them, but there's no reason to try and have one in your basement. So, okay, the other building stuff part, I feel like Monika and Will are better suited.
I mean, I think, there are always the technical challenges of sort of dealing with, noise and dissipation, right? And I think maybe the second one is kind of worth commenting on, because this issue of even sort of understanding better what one can do in open quantum systems, I would say is I think one place where there's a lot of opportunity. And in part that's because in any case, ultimately a quantum computer, if you're doing error correction, needs to be open in some way, even though we sort of like to think first about building the most closed system we can. But ultimately, you need a way to take entropy to effectively cool the system, right? And in practice, certainly in my lab, we try to make, for example, these cavity QED systems as closed as we can, but in reality, there's always a little bit of light that's leaking out, and that is a source of decoherence. But maybe there are also ways of using the openness. And so for me, sort of on a, aside from just the technical challenges of making the noise as low as possible and the system as closed as possible, I think there's an opportunity for really kind of also understanding, maybe on the theoretical side, what are the ways that one can also sort of harness or understand the openness of the system.
Yeah, maybe I can just add a few perspectives from the systems engineering side. That one thing that I find very exciting about quantum computing today is that it is starting to become a systems engineering problem. And what I mean by that is that there's a trade space, there are knobs that we can turn, and there are effects that happen because of those knobs, right? And we're able to trade things off depending on our system or what we're trying to achieve. And that happens across the entire architectural stack, all the way from the software and the algorithmic layer down through the compilation layer to the error correction, error mitigation, and then even down at the fundamental physical hardware layer. And so, you know, if the question is, you know, what are the barriers to achieving practical quantum computation at scale, I think you'll find, you know, that it's in and of itself is a 60-hour, 60-minute talk, but it really spans that whole vertical stack, that architectural stack. And we're learning about new barriers as well as new solutions every year. But the exciting thing for me is that it is now a question of systems engineering, or at least it has this aspect as well, in addition to the fundamental science. The fundamental science is still very important, but now the quantum engineering of these systems is coming into play.
Okay, good, thanks. So I'll grab another question, and this one actually comes from an undergraduate, so we'll return to the student perspective. And this undergraduate student is studying nanotechnology and has a background in MEMS fabrication and thin film deposition. And this person writes that I would like to break into fabrication techniques for quantum circuits and quantum materials. What are the steps one should take, as I don't have any theoretical background in quantum physics? And if you could answer this question and maybe your view for training a quantum workforce, starting at the undergraduate level, how you view, us as researchers can engage in that, and how, or what partnership you might see industry playing in developing a pipeline of quantum science researchers, engineers, and technicians for the future.
I can maybe comment on the undergraduate education aspect. So actually one of my kind of, most satisfying experiences has been developing a freshman seminar on quantum information. And I did this because I had this feeling that there are so many students who are curious about quantum information or could get excited about physics if they learn about quantum information. But the usual path to even getting to quantum mechanics takes, about 3 years, depending on the details of the program, right? And because you go first through all the classical physics and so forth before you get to some of this exciting cutting edge material. So it turns out, though, that you don't really need to take that path. And you can understand qubits with just linear algebra, right? And so it's sort of, for me, it was actually kind of a revelation to realize that there's a totally different way of getting to these cutting edge topics that in just a 1 quarter course, I was able to start by introducing concepts of qubits and quantum measurement, quantum key distribution, and get to quantum algorithms. And at the end, some of the students were, in their final project, basically programming quantum algorithms on, the IBM or Rigetti platforms and things like this. And so, and in fact, teaching that I was teaching things that actually my graduate students didn't know. So you can rapidly really get to kind of frontier topics in quantum information in a way that circumvents a lot of the like many years of physics background. And so I think that's actually important because that is something that will allow people from different fields to contribute, right? So if you're taking a heavy course load in computer science or chemistry, well, chemistry you'll get to the quantum anyway, but let's say computer science, and in fact, even in a course load in physics, you might not get to talking about entanglement. A standard quantum mechanics course never gets to that, right? So I think this is something that it is possible to get to quantum information topics much earlier in undergraduate education, and I think that we should be doing more of it.
I just want to say, I kind of want to take your course now.
Well, now that I have to do it online, maybe I can make it publicly available. So
That would be awesome.
Yeah, maybe one thing to add is that, you know, part of this move towards quantum engineering means that we have the opportunity to develop the engineering abstractions that we found so useful, say, last century when we talk about lasers or semiconductor transistors. You know, the people who first invented and developed the theory around that really had to use quantum mechanics to understand it, even though it was fundamentally a classical device. But over time, you know, the following decade or two, we figured out how to abstract that down to the knowledge that we really need to use and understand and then apply those devices to different fields. And I feel that even though qubits themselves are quantum mechanical, and that's different, that these engineering abstractions can still be made. And, you know, we're seeking at MIT, I would say, to identify places where we can inject these types of ideas into our existing undergraduate curriculum. You know, one simple example is in an introduction to probability, which I am teaching. We can introduce many concepts that later may come into focus once one learns quantum mechanics, but one doesn't need to know quantum mechanics in order to actually do some of these problems and in a meaningful way and still teach the course that we're trying to teach.
Great, thanks. And then Danna, I don't know, do you have another question? Okay.
Yeah, let me take one of the other questions from the Q&A, and I think, but I really like these directions about education. I might grab another one of the pre-submitted questions after this. So another question about, I would say, the timeline, which I think in a sense all these questions tie together, right? The timeline, the hype, is what would you say is the bottleneck currently in quantum computing research? How large is the gap between quantum computing theory and the implementation of those quantum algorithms and such in physical qubits? How does the dynamic between theory and physical implementation of quantum computing compare to the analogous dynamic in the historical development of classical computing?
I'd call this like the 80s of quantum computing. Is that a fair estimate for, at least for, I don't know, a timeline? So, well, do you agree?
Game. Can someone make me a quantum computer game?
So there are games out there, and in fact, they help also in the context of teaching and teaching, especially for students who are K through 12 and may not even take, you know, a course in quantum mechanics or need to be convinced that they need to take courses in STEM, right? So I think there are games out there, and I think Entanglion is one of them, teaches you about entanglement, but it's just fun to play as well. So you should try it.
I'm not sure.
Serious aspect. Go ahead, Monika.
I'm not sure I quite agree with the 80s. I mean, in the 80s, classical computers were already quite useful, right? And I think in the 60s, they were already helping with space flight, right? So maybe this is more like the era of the kind of the vacuum, I don't know, sometime, I don't know, the vacuum tube era or something, where it was like filling a whole room and you were using punch cards to program, I don't know. So I think there's still you know, much room to develop maybe before we even get to the 80s, but we'll get there.
The blowing match is the 80s.
Yeah, well, you know, and to make quantum computers that we find to be useful and solving real problems, of course, we need to make those systems robust and reproducible. And to do that, of course, we need to have the fundamental qubits themselves have higher performance. And clearly that is absolutely a barrier today. And it has to do with science. It also has to do with fabrication, engineering, material science, things like that. And so that's clearly important. If we don't make advances in qubit performance, it's going to be very hard for us to realize a quantum computer in the future. At the same time, it kind of rubs me a little bit the wrong way when people say, okay, I demonstrated this, now it's just engineering, right? And just as if that's going to be the easy part. Even when we make these qubits highly robust, right? Individually, building them into a system is in itself an entire discipline called systems engineering. And that's not easy either. But I would say if I had to identify the one thing today that is a barrier, certainly the performance of individual devices remains a barrier, even though we've made such remarkable progress over the past 10, 15, 20 years as a community. They need to be better if we're going to build large-scale, robust, reproducible systems.
I think there was a question about can we draw analogies to the history of classical computing, and I wonder actually whether there's an analogy to the field of machine learning. So there was a long history of sort of theory on artificial intelligence, and I think even the name artificial intelligence kind of went out of fashion because there was, the ideas were out there, but they weren't really realized, right? And then the hardware caught up to the point where you actually can implement these amazing machine learning algorithms that recognize dogs and cats and faces and all these things that just wouldn't have been possible without the hardware, actually. And so I'm definitely not an expert in this field, but my understanding is a lot of the ideas were there, and it just took time for the hardware to catch up.
Thanks. And then the next question, given that we're in this IIN symposium and the health and ethical implications of nanotechnology has been debated and discussed extensively over the last decade, I'm curious what each of you think or view might have whether or not your research has ethical implications in the broad category of quantum information systems. How do you view what you're doing and possible implications in terms of ethics? Or if you've thought about this before.
Yeah, maybe I'll just say a few things. Absolutely, there are ethical implications for science, I think in all fields, not just in quantum computing. But a couple areas where I find myself, thinking about is to the extent that quantum computing is implementing machine learning or AI or optimization, clearly many of those same issues that one may identify with conventional or classical AI will apply also in the quantum computing domain, right? And, similarly, with classical AI or machine learning, it may not be possible to trace back the origin of a particular decision thread that happens, or the precise neuron of the neural network that leads to a particular result, which decides how the car drives or something like this, right? And clearly has implications for injuring people and whatnot. But a quantum computer also, of course, when it's at scale and truly gives us promise, it is a machine where we cannot know, right, the quantum state of the machine. Like reconstructing that quantum state is practically prohibitive, if not impossible. And that is what underlies the power in the first place, right? And so, quantum computing will create machines where answers come out and we're not sure, or we may not be able to trace back precisely how we got there. And in many cases where there are heuristics involved, like optimization, of course, we never even know if the answer is a true minimum or a true maximum, right? We only know it's better than the answer I got before. So again, tracing back the particular lines of the code, right, to use a figurative language, that got us from point A to point B with a quantum computer is not going to be possible. We understand the architecture and we understand the program, but what actually happened in the machine, we're not going to know that.
Yeah, I guess maybe I'll just add my thought that essentially any powerful technology can be used for good or for evil. Certainly there's a reason why the military is interested in quantum sensors, right? And so then if you're making quantum sensors, you might want to think about what they're going to ultimately use them for, right? Now, I almost think though, but we can't just say I'm going to stop developing this technology because I'm worried that it will be used for something that I have ethical, concerns with. I think we have to develop the technology, and then we have a separate obligation as citizens, right, to think about how the technology is used. But
I think
if you don't develop it, somebody will, right?
right.
So, yeah.
I think that's an opportunity actually to collaborate with folks in the social sciences who think about the impact of various technologies. And I think there are a few different things here. Of course, we'll talk about the decision tree aspect and the military aspect from Monika. There's also the widening equity gap that access to an advanced technology like quantum computing is furthering, right? And the questions that have come up also in the context of education here highlight that not everyone has immediate access to research in this field or access to faculty who can train them in this area. And I think that's something to be cognizant of. And I think a good area to collaborate with social scientists from the beginning rather than say partway through where that needed to happen, say in the case of AI. Right? So.
Great. Yeah. Thank you for those comments. Enlightening.
Thanks. I think that's probably all the time we have. So before we close the conference, I'd like to once again thank all of our distinguished speakers for their outstanding presentations and the really lively discussion here. I'd especially like to thank all of you for joining this third Frontiers in Nanotechnology virtual mini conference. Look for the Frontiers virtual conferences to resume in the new year. In the meantime, the new academic year. In the meantime, I invite you to join us on October 29th for the IAN's annual symposium, chaired by IAN Director, Professor Chad Merkin, and featuring 4 world-renowned speakers, Jim Gates Jr. from Brown University, Bert Meyer from Eindhoven University of Technology, Jill Millstone from the University of Pittsburgh, and Ted Sargent from the University of Toronto. More information can be found on the IAN website. It's IAN Nano, but there's only one N, .org. Have a good afternoon. And thanks, everyone.
Thank you.
Thanks everyone.
Thank you. Thanks, Monika, Prineha.
Thanks, Will.
See
See
you later.